That's a kind of a law which is very much in the in the offing, right? You have to tell me as a part of your class exercise, right? What will be the effect of such a law? And do you think there are any other alternatives, avenues, which can actually make domestic servants, domestic helps better off? Right? Okay, can you, on the basis of what you've learned in this class? Is clear? Sure? Okay? Right, so we'll have some time for doing this, maybe a 15 or 20 day gap, and then we can actually have a classroom discussion on this. Right, on optimal contracts and what you see around, right? So, correct. So now we go back to our mixed strategy Nash equilibria, which is a video which we have mixed up. Okay? But please remember, economics now, so as we go on to more and more into this, going to become more and more formal, more and more technical, but more and more useful also. Right? So it will now no longer be as simple as the first module was. It's going to become, it's a lot of derivatives, a lot of arguments, a lot of counter arguments, a lot of things a lot of subtlety in the arguments. You need to really think over those arguments to understand those arguments carefully. Right? Okay? And so that's important that you learn to make very subtle, because when you say that it's actually creation of alternative opportunities which makes work better. In the sense, gives people better wages and makes them work less hard. You're actually making a very complex argument. Right? Because we actually said there's a utility function, we put certain structures, we derived certain things. Right? So it is not an argument which you're making just from the top of your head. Right? Increasingly, you will learn to make in this module, in this course, you essentially learn to make these kinds of arguments about the real world. Right? And that's how economists think. Or that's how economists ought to think. Right? People who claim themselves to be economists, this is how you ought to think. Right? Okay? So we will learn to think about that, and you can't really learn to think about it like an economist without encountering the subtleties of an economics argument and the complexities of an economics argument. So you must also prepare yourself that there is going to be a lot more complexity now coming into this class than has needed to be, because economics is a complex subject. Okay, so now coming back to, so think of, say, the battle of the sexes game. You have the husband, the wife. Okay? A boxing match and a cricket match. Right? Boxing and cricket. The husband wants to, or say boxing and or say cricket and opera, right? Cricket and opera was the one which we did in class. And I said, okay, let's make change in cricket and right? Cricket and opera. Okay? So the husband wants to go for the opera still, and the wife wants to go for a cricket match. Right? So the husband goes for the opera and the wife goes for the opera. The wife gets 4, the husband gets 3. Because he would much have to go for the cricket match, but he wants to be with his wife. If the husband goes for the opera and the wife goes for the cricket match, right? Say both of them, husband goes for the opera and the wife goes for the cricket match. Say both of them are sadder than what they would have been. But the wife is relatively, because the husband goes for the opera, or let me put it, say 2-2. Yeah? Let me put it 2-2 and let me put it 3. All that I want really to make sure is that there are no dominant strategies. Right? This husband-wife cricket opera is actually a parable. Right? I could put any story around and get a game. The essential part of this structure is that it should have no dominant strategy and 2 Nash equilibrium. So any set of numbers will have that. I tell you all this story of husband-wife cricket opera because we need to write those, you need to understand, you need to have some context on it. Right? So in this case, there are 2 Nash equilibria, OO, right? Because if this is the case, nobody will have an incentive to unilaterally deviate. 3-4, CC is another Nash. Nobody will have an incentive to unilaterally deviate from that, right? Okay, there are no dominant strategies for any player, right? Okay, sure. Now, what is the kind of Nash equilibrium we've thought so far? I've said that the husband has two strategies, O and C. The wife has two strategies, O and C. So wife can either do O or C. The husband can do either O or C. But we have not thought of a situation where the wife does O with a certain probability and C with a certain probability. And the husband does O with a certain probability and C with a certain probability. Which are random. So we have not thought of the wife and the husband randomizing over O and C. So you can think of the husband tossing a coin and say if the coin comes heads, I will choose O, and the coin comes tails, I will choose C. Right? The wife saying, I am going to go and if it rains tomorrow, I am going to see O. If it doesn't rain tomorrow, I am going to say C. It's a strategy. Right? It's a strategy because it's a way of behaving. It's a way of choosing. It's a way of choosing an action. The way of choosing an action is a strategy. So you have actions and the methods through which you choose actions, the rules by which you choose actions are strategies. So choosing O always or choosing C always with probability 1 is one way of choosing. But there could be ways of saying that I am going to choose O, right, with a probability say P, I am going to choose C with a probability 1 minus P, whatever that P could be, right, is another strategy. Such strategies are called mixed strategies. Okay, so mixed strategies are actually probability distributions over pure strategies. Right, and if you look at Gibbon's book carefully, you will find good definitions of this. Right, but I want you to understand the intuitive part of it. That is, if you, right, okay. Like, I will choose to bat if I win the toss. Is a pure strategy, right? So for example, is a strategy that you can have. I will choose to bat if I win the toss. I will choose to bowl if I win the toss. Right? Is a strategy that you can have. But you can also have a strategy which says that if I win the toss, there is a 30% chance that I will choose to bat. There is a 70% chance that I will choose to bowl. Right? If I win the toss, I will look at the ground conditions, I will look at various other things and then decide what to do. So what I am really doing is I am randomizing over strategies. Right? So that could also be a strategy. Right? So let us think of, and therefore if you think of Nash equilibrium pure strategies, there will also be Nash equilibrium mixed strategies. In fact, there is a theorem which says that every finite game will have a Nash equilibrium, at least one Nash equilibrium in mixed strategies. It does not necessarily have an equilibrium in pure strategies, as we know in the Holmes-Moriarty game, right, where you don't necessarily have a Nash equilibrium. So let's find out how we can find out Nash equilibria of mixed strategies, or mixed strategies Nash equilibrium. So let us say that the husband plays O with probability P, C with probability 1 minus. Let us see that the wife plays O with probability Q and C with probability 1 minus Q. Let's find out if we can solve for P and Q. Right? So now if the husband plays O, he gets 4 with probability P. Right? So let's write this. Okay? The husband's payoffs from playing O is 4Q plus 2 into 1 minus Q. Yeah, if he plays O, if the wife plays O, he gets 4. If the wife plays C, he gets 2. So he gets 4 with probability Q and 2 with probability 1 minus Q. Right? Which is 4Q plus 2 minus 2Q is 2 plus 2Q, which is increasing in Q. Right? Oh. What is the husband's payoff from playing C? 2Q is equal to 2Q 3 minus Q. Right? Which is decreasing in Q. Right? Which is decreasing in Q. Now, so if I write the husband's reaction curve here, if I write the Q here and P, right? The husband is indifferent between the two strategies when I have 2 plus 2Q is 3 minus Q, or I have 3Q, okay, is equal to 1, or Q is equal to 1/3, right? So at Q is equal to 1/3, the husband is indifferent between H and O. Beyond Q is equal to 1/3, the husband is better off playing O, because his payoffs from O increase with Q. For Q less than 1/3, he is better off playing C, right? So he will play C. So if I put Q is equal to 1/3 here, okay, right? For all values of Q less than 1/3, he'll always play C, right? He'll always play C, so P will be 0. Right? So my points will be like this. Okay, for all values of Q. For all values of Q greater than 1/3, he will always play O. Right? So if I put 1 here, if I take this, the husband's reaction function will be like this. HRF. Right? Because husband reaction function will be like this. For all values of Q greater than 1/3, P will be 1. Is it not? Okay, the diagram is not coming. Yeah? Alright? So you see now again, look at this diagram. Right? So if you look at the husband reaction function, right? For all values of Q less than 1/3, the husband is strictly better playing C. Therefore, P will be 0. Right. So, his reaction curve for Q less than 1/3 will be this. For all values of Q greater than 1/3, the husband is strictly better off playing O. Therefore, the probability which he plays O will be 1 for Q greater than or equal to 3. So, his reaction function for the husband will go like this. Right? If you want to draw, now let's see how we can draw the wife's reaction function. Okay, so let's pan the camera a bit again. Right. So let me now do the wife's reaction function. So I have, if the wife plays O, what did she get? 4P plus, no, she gets 3P, you're right. She gets 3P plus 2 into 1 minus P, right? Which is 3P plus 2 minus 2P is equal to P plus 2, right? Oh, wife's payoff from playing C is equal to 2P 4 into 1 minus P, which is equal to 2P plus 4 minus 4P 4 minus 2P. So her payoff from playing C is decreasing in P, her payoff from playing O is increasing in P. At what point will the wife be indifferent? When you have 4 minus 2P is equal to P plus 2, or 3P is equal to 2, or P is equal to 2 by 3. Right? P is equal to 2 by 3. So for P greater than 2 by 3, the wife is strictly better off playing O. Right? So if I put 2 by 3 here, okay, for P greater than 2 by 3, right, this will be 1. So if this is 1, right, for P greater than 2 by 3, the wife will always play Q. For P greater than 2 by 3, wife will always play O. wife will always play O, that is Q will be 1. Right? Q will be 1. Right? It's coming?
Yeah.
Okay. Q will be equal to 1. And for P less than 2 by 3, Q will be 0. Right? So this line, okay, to make it better, I'll make it like this. The red line is the wife's reaction function. Now there are 3 points on this reaction function. Right? So this is Q is equal to 1, P is equal to 1. That is Q is equal to 1, P is equal to 1. This is that equilibrium. This is P is equal to 0, Q is equal to 0, which is this equilibrium. And then there is a mixed strategy equilibrium here, where the wife plays O with probability 1 by 3, C with probability 2 by 3, husband plays O, right, with probability 2 by 3, and C with probability 1 by 3. So you have a third mixed strategy Nash equilibrium here. You have a third mixed strategy Nash equilibrium here. Is this clear? Can you now solve for Nash equilibrium, mixed strategy Nash equilibrium? Right? So how much more time do we have? Do you all have any difficulties over this? Anything that you would like me to go over again? Is this clear? Sure? So thank you very much. The reference for what I have done remains the same. And introduction to, you can see this on the video. Right? Is it visible? Excellent. Yeah?